I'd like to introduce, though obviously no introduction is needed, for Chandler Carruth from Google. He's going to talk about Clang, MapReduce.
Thanks. Thank you. So I'm here from Google. I'm here to talk to you about some of the really crazy stuff we're doing with Clang here at Google. Now, one thing I do want to say is I actually work on an unusual team at Google. I don't work on search. I don't work on like Gmail. I work on engineers' tools. I work on infrastructure for our own developers. And that means that other software engineers are my customer day in and day out. And that's both really great and really terrifying because they also know where I sit. And that worries me some days. But one of the interesting things is that about 2 years and a month ago, I had this really crazy idea. I was talking to a manager. I was like, we need to use Clang at Google. We could do a lot of really great things. We have a lot of C++ code, a lot of bad C++ code. We could really use Clang. It'd be wonderful. And I was specifically trying to get this guy in the front row to use Clang at Google. And I kept talking to the manager about how great an idea this was. And finally, he turned around and was like, all right, fine, it's your project now. Which wasn't exactly my original intent, but it worked out pretty well. We started using Clang, and it turned out that we were able to do a lot of really amazing things with Clang. And for us, last year was kind of the year of Clang diagnostics. This just changed the way we thought about C++ at Google. It was a really, really revolutionary period of time because we stopped trying to worry about C++. How do we cope with C++? How do we keep C++ from hurting our developers? And we started looking at like, okay, how do we help our developers? How do we make C++ a better experience for developers? And that was a remarkable transition to occur, especially at a very large company. But the compiler is only one tool, right? And Doug actually had this great slide that, funny thing, ends up in my slide deck as well. Clang is not about one tool. The compiler is one tool, but Clang is about something much more than that. It's about a tool platform. It's about the fact that we can build a lot of different tools on top of it. And that's really, really powerful. And we've worked on diagnostics, we're working on other tools, we're working on one-off tools, we're working on plugins, we're working on these things, but there's one tool that was just uniquely googly. There was one thing that if Google was going to build a tool on top of Clang, we were going to build a MapReduce tool on top of Clang, right? We have to dial the tooling to 11, all right? And so we did that. Now, unfortunately, some people are not that familiar with MapReduce, so I'm going to start off this talk by giving you guys just a little bit of context. What are we talking about when we talk about MapReduce, and why does Google even care about this? So you might be familiar with the functional programming concepts of map and reduce. The idea is mapping some custom function across a set of data and producing a new set of data. And the idea of reducing is using a single function to combine a set of data into some single value. All right? Now these are very, very standard functional programming constructs. You can find them in Python like I have. You can find them in a lot of other languages. One of the interesting aspects is that this forms a reduced computational model. If you can express a computation using this model, that's really powerful because it reduces it so far that we can do very interesting transformations to your computation. We can automate a lot of the processes of changing how the computation takes place. All right, and of course, what Google does with MapReduce, what Google uses this freedom to achieve is to scale your computation up to a cluster. How do we run it on not one machine, not 10 machines, not 100 machines, but on a data center full of machines? All right, and that's a very, very powerful thing for us. It gives us a great deal of freedom to scale up a computation and to make it extremely efficient at scale. Now, the way this looks once you move it up into a data center is something like this. You start off with a very large distributed data set. And you're going to map each element in that data set on a whole lot of machines into interesting data. And the interesting data is structured specifically to help the MapReduce function work. It's structured as key value pairs. All right? Once you map it into particularly interesting key value pairs, MapReduce shuffles all of these key value pairs around so that you can then reduce the set of values for any particular key into some single piece of data. And you can store that, all right? And this is how we use MapReduce day in and day out at Google. This is what we're using it for. It's for very distributed computations that transform and then reduce data to something interesting. Now, one of the key observations about MapReduce, especially at the cluster scale, is that the interesting parts not the map and the reduce. The interesting parts for MapReduce is the infrastructure. How do you scale it up? How do you manage the machines? How do you optimize locality? Right? How do you actually make the computation as efficient as possible? Well, for us, because we're working on Clang, we're not working on MapReduce, that was actually great, because it meant there was this nice little slot where user-provided code belonged, and everything else just existed for us, right? We got all of the MapReduce infrastructure and all of the power and the scaling of this for free from other teams at Google. And Clang is beautifully suited for this. Because it's built as a library, because it's built to be integrated with other systems, we can slide Clang into that map phase. We can slide the Clang logic in wherever it makes sense for our computation, and suddenly we've scaled up C++ computation to a data center. And that's really powerful. But before we go into too much of the power that brings us, we need to take a step back. We need to think about what problems would Google try to solve that would require a data center's worth of C++ computation? Because that's a lot, right? Unfortunately, Google suffers from a strange problem. We have too much code. I can't express to you enough how much of a problem this is for us. And this is just Google-authored code. We have over 100 million lines of code, and our largest programming language is C++. Now, Google hasn't been around for all that long. So this code base has grown fast. At times, it's grown very ugly. And to make matters worse, we didn't just write a lot of code. We didn't just build a lot of code. We build it. We build everything from source on the main line of the code base every single time. We don't have precompiled libraries. We're building all of this source all the time, every single build. That's insane, okay? It is truly insane. But it presents some opportunities. Because you can imagine the LLVM development process, but 50 times larger in multiple dimensions, 50 times larger, 50 times more people, right? 50 times more code. And you can imagine that this is going to be really interesting because now we can actually evolve APIs that are used across a company. And I don't just mean in terms of bringing in the new generation of API. We can deprecate APIs. We can find buggy APIs and actually proactively fix them. We can change code that was written poorly a long time ago. And originally, it may not have even seemed like a bad idea, but we can learn from it and we can evolve the APIs iteratively. But in order to do that, we have to scale up our entire development process. And we do that at Google through the standard Google scale ideas of self-service, automation, and cluster-wide computation like MapReduce. All right. So what we're really talking about at this point is a search engine for C++. We're trying to apply the same concepts we use to search large sets of data on the internet in order to understand a large code base. So what we're really driving at is a Clang-based engine for analyzing our C++ code, for understanding what it does, how it works, and how it can be made better. Well, funny thing, I know a few people who know a thing or two about building a search engine. So we can go and talk to them. We can figure out, okay, how would we architect a search engine on top of a C++ code base? Well, the first step is you need a crawler, right? Everybody loves the crawler. It's what goes around, downloads all the websites, right? Well, we needed a crawler. And at Google, our crawler fell out naturally because we build all of our source code from source every time. So our crawler is the build system, all right? It runs in a data center out in the beautiful cloud. We compile everything. We link everything in the cloud. It's wonderful. It's amazing. There's a whole blog post about that. But what we can do for Clang, and what we can do in building this pipeline, is we can actually instrument the compile. Every time a compile takes place, we can actually record what went into that compile. What files were part of it? What was the command line? How did it work? Exactly how did Clang enact that particular compilation? And when we record that into a large distributed data storage layer, we can then rotate that layer and start using that as part of a MapReduce to do queries. Because now we have a record of every compile that took place. We can query across it, right? We can reduce the data that comes out of that query into the key things of interest. And we've got a really powerful C++ search engine-like pipeline, okay? And so this is what we've been building for a while. We've been building kind of a mini search stack for C++ code. But throughout this, I'm mentioning the C++ query. I'm mentioning that there's something we want to know. And Doug even talked about the fact that sometimes you just want to understand certain parts of your code. And one of the things we ran into trouble with is how people actually formulate those queries. Because for a long time, people have gotten by with a kind of textual query, which is really, really problematic. And it's ingrained in developers, right? Because grep is awesome. And so they're not going to give up grep. and they're going to look for, an element, and they're going to try and make it better, and they're going to add some fancy regular expressions, and they'll add some more regular expressions. It starts getting really horrible, and by the end of it, they've basically tried to implement a mini C++ parser in a regular expression. Like, I can't even count how many problems they have now. And it's really, really challenging to get them to stop thinking about that and to back up, because they didn't actually want a textual query. What they wanted was a semantic query. They had a concept that they were trying to find. Now, it's not a simple concept. In this case, it's a very complex concept. They're trying to understand some core semantic concept of C++, and we need to give them a way to write that query. They want to match a particular class, right? We're going to call this element space, right? And it's not just any class. It's a class that provides some interface. And it's an interface that's been extended by other classes, and it's in use. And what they really want to do is they want to match the uses of this interface, because this interface was bad. They used the word get for getting an element of a container. But which element do you get? What they actually wanted was something else, right? And we need to find uses of this overly generic interface, and we need to fix them. We need to take code that looks like this. We need to make that get turn into something a little bit more sensible, like front. But to do this, we can't just change one piece of code, right? This is a source-to-source translation. This is a very complex source-to-source translation, and in particular, you are not going to use a regular expression to pull this off. It's too hard. Okay, so when we're talking about automatic source-to-source translations, we need some powerful tool to do that. And the good news is that, well, we've got Clang. Clang is, of course, the tool we want to enact source-to-source translations and to enact these complex queries. But if we just sit down and we try and write out the code, right? If you watch Doug's talk and you see exactly how you write out the code, the easy ones will be beautiful. But as you get to really complex ones, the code will start to look like this. If you've ever looked at the insides of Clang, this will not be unfamiliar to you. You've got to do a lot of manipulation. You've got to check for a lot of different patterns. You have to, walk over different fields. There's a lot of complexity and a lot of complexity that's really inherent to Clang. And this isn't a problem with Clang's interface. This is the AST modeling all of the complexity of C++, right? This is just the inherent complexity of C++. But by the end of it, right? By the end of it, we have so much code that we have no idea what we're doing here. This function is recursive too, right? It's really challenging to write complex and precise queries over the AST. And it, in particular, it doesn't scale. If we want people to write tools like this, we've got to make it easier. Okay. So we need a good way and an easy way to express C++ queries using Clang for developers to actually use. We know that regular expressions aren't enough, right? They aren't powerful enough. They don't work over trees. There's no realistic way to map them into a proper C++ query. Some people have looked at using something like XPath, right? Because XPath was at least designed to do structural queries. But it's designed to do structural queries over, XML. It's designed to do it over a tree data structure. And it's also kind of horrible to use, just a little horrible to use. One of the most attractive ideas we looked at was a pattern language, because if we could kind of, grow a pattern syntax inside of C++, then engineers would inherently know how to use it, because they know how to write C++ already, right? They just need to inject patterns. Unfortunately, this is really hard to define. It's really hard to make it correct and safe and easy to use. And even harder is to come up with ways to express implicit C++ constructs as patterns. What if you only care about matching default constructor calls? There's not always a single token anywhere in the program that signifies a default constructor was called here. How do you write a pattern to capture that? So what we're really driving at is that we need some tree-ish matching language. We need some way to actually isolate a tree of the AST. So we took an idea from some testing libraries. If you've used unit testing libraries, especially in other languages than C++, you may be familiar with it. They have matcher libraries that form generic predicates over values, right? And you can use these when setting up your expectations to make them sufficiently general to not break the moment someone breathes on the library implementation, but still actually ensure that you get the results you're expecting. And if we think about the AST in Clang as a value, we can imagine coming up with a predicate library, a predicate matching library, targeting those values. The really interesting thing is we can actually derive all of the predicates we need from Clang's own AST. you can almost invert the AST and turn it into a set of matchers for those AST nodes. And as we do that, we end up coming up with really easily composable matchers. It gives us a great point to kind of unify common patterns that people want to match again and again inside of a specialized predicate that handles that logic. And so I'm going to try and walk through an example of how this can be used to really easily isolate a subtle pattern inside of C++ code. So the example code I have is a particular method call. We're calling that pesky get method. And in particular, there's other code around here that might look similar to that at various different points, right? There's another get method call that's actually a totally different get, right? There's a cook call. There's some other code in here. We want to isolate the interesting piece. So using our matcher predicates, we first off want to find some call. We're looking for some call expression. We want to narrow that a bit to actually look at the callee and make assertions about what callee we're actually referring to here. We can add an assertion that this callee has to be a method, not just a function, and that removes one of the false positives of this match. We can then make sure that it's a method with a particular name to filter out another case where it's actually not what we're looking for. But we've still got two here. There's still two that actually match this. We need to extend it. We need to actually start matching what the type is of that method, like what this pointer's type will end up being. We can say that it's going to be a class. We can extend the class predicate to say that it's derived from some interface at some point in its type hierarchy, and we can name that interface as element space, and suddenly we've actually isolated that one piece of the code that we're looking for. Okay, and this is a really, really easy to teach a developer about language, and it's a lot easier to reason about and to understand when you're reading the code than a lot of if statements. Now, we need to go one step further, though, because we don't want to just isolate something. We also want to be able to refer to it. One of the key things that the kind of procedural code is doing is it's not just removing false matches. It's also digging out pieces of data about the tree matched in order to use that later. And so we can do that by kind of saving pieces of this AST as we're matching it and giving them names. And so we use an ID to kind of bind a name to some AST element that we're matching so that we can refer to it later. All right, we have this elegant way, I hope elegant way, of matching a particular pattern in C++ code. So let's back up a second. What are we doing? We're trying to transform all of the code that looks like this, and we've already figured out all of the code, right? We've already solved the first of Doug's examples. We've already been able to, find all of the uses of this. We can print them out, we can locate them, we can go shake our fists at developers. But let's do a step better. Let's actually take it all the way and let's try and do the source-to-source translation. We actually want to transform the bad C++ code into something better. We want to make it say front here instead of get. And we can do that using the same tools, especially when we have Clang. It has the rewriter interface. It has all of the power we need to actually go in and directly rewrite it. So when we pull all of these pieces together, we get a pipeline that looks something like this. We start off with an index of our compilations, all of the compiles that are relevant. And we take this particular compile, we run it through this AST matcher library in order to isolate the interesting bits. We have a callback then that's registered for every single interesting piece of the AST to go in and do a source-to-source translation to rewrite a piece of it. But rather than applying that rewrite, because we're running in a very distributed system, we simply serialize it. Right? We write out in one of those key value interesting pieces of data a file name that has a match in it and a particular edit that we would like to apply to that file name. Right? And as we're going through and doing this, we get all the power of Clang because we can connect Clang to our infrastructure. And in particular, we get to use the rewriter and the matchers to combine and kind of tag team the problem of doing the source-to-source translation. Inside of our callback, we can dig back out that saved expression, that saved member expression. And we can use the rewriter interface to figure out exactly how the rewrite should look. And then we just come up with a serialization scheme in order to write it out as the value of a key value pair. All right. And then something really cool happens. We've written out one edit. but we have a lot of edits we need to apply to a very large code base. And this is where the MapReduce framework kicks back in. As we're serializing these edits, MapReduce understands how to move the edits around and work with them because we've written them out in this key value form. So we get the file name, we get the edit operation. MapReduce is going to consolidate all of the edit operations for a particular file. It's going to hand it to a single process that can look at all of the edit operations. It can compare them, it can deduplicate them, it can see if there are conflicts, if two edits are going to stomp on top of each other, resolve anything that it can resolve, and produce a brand new piece of source code that reflects the desired edits to that file. All right, so this is the high-level picture of what we're doing, right? We're bridging a full end-to-end pipeline of source-to-source translation using MapReduce for our infrastructure and Clang for all of our business logic. But there's one more thing that I really want to clarify for you guys. How long does this take? Because one problem we had is that we did this for some developers, and we kind of demoed this process to them. But it took them about 4 hours to run it over just their project's source code because it ran on one machine. And that was running on every single thread that machine could run. So we needed to find out exactly how quickly we could let people do this. The other thing we found was that they aren't going to get it right the first time. They're going to write one of these. They're going to need to run it over a lot of code and find all the long tail of edge conditions that they never thought they needed to handle, right? And so they're going to have to iterate on this process repeatedly. And if we don't make that easy, if we don't make that a tractable problem for them, they're never going to use this platform. It takes us 10 minutes to transform from source to source every single C++ file at Google. That's over 200,000 compilations taking place, on the order of 10 billion preprocessed lines of code running through Clang, on the order of 100 billion tokens running through Clang, producing on the order of 100 billion AST nodes. All right? It's that scale of problem, and that is why we need MapReduce. So what's next? Google's crazy, right? And so our code base is enormous, and that's true, but there are a lot of other code bases that can benefit from the same tooling process without necessarily the number of computers involved. And so we really want to scale this whole thing down to make it reasonable to run over small open source projects, and by small I actually mean the size of LLVM and Clang, not small as in like bzip. We also want to try and package a lot of it up. We want to make it very easy to use because it turns out that a lot of the transformations you do are shared between different things. You want to inline a method, you want to extract a method, and then you want to do some custom operation to it. And so having canned transformations would be really helpful. We want to try and do automatic reformatting. So we apply all of these edits, right? We should actually be able to load Clang back in that reduce phase to reformat the code that we've edited, to check it and verify that our source-to-source translation actually worked, to give the user a better idea of what resolution is necessary when we have edits that conflict, that don't actually apply simultaneously. And of course, and perhaps most importantly, we need to open source this. So we've been working for the last few months on trying to re-architect the actual code that implements a lot of the functionality here, make it acceptable to upstream, and we're hoping that's going to be going upstream over the next few months, and you guys can start playing with a lot of the same things. One of the interesting things is we already have a plan for how to scale all of this down and make it really easy to run kind of on your local project on your local machine. And so believe it or not, that's what I had. But I suspect there will be more than one question, and so I'm going to go ahead and jump to the questions. So can I mention some of the most common uses of the tool? Absolutely. One of the first uses of the tool, and I didn't actually see this one coming, was they wrote a tool to walk over our code base. So you're familiar with, hopefully, with LLVM's string ref class, if you've ever touched the code base. Well, it's just kind of a nice, polite wrapper around a character array so that it doesn't matter where it came from. Well, we have the same thing inside of our code base. We have, I swear to you, the API is frighteningly similar. And just like LLVM's code base, this class didn't always exist. We had about 5 years when it didn't, and then we had a lot more years where it did. And so there's this mixture of code that assumes the existence of this, and this mixture of code that assumes that actually every single function parameter accepts a const standard string. And so we wrote a tool that actually goes over the code base and it finds every place where you call .cstir or you actually construct a temporary string object just to pass it to a function parameter, when that function parameter actually doesn't need those type conversions because it has one of these automatically converting string wrappers. And it deleted thousands and thousands of redundant string copies from our code base, which is really cool. We actually ported that tool over to the open source stuff, and we've already mailed at least one patch to Elvium and Clang doing the exact same thing to Elvium and Clang's code base. Some of the other really common use cases we had. I'm trying to think of the ones that would make sense. So we've had a lot of custom ones. We had teams that had developed a bad interface and they needed to go in and fix it. And in particular, we had one interface that was used throughout our code base. I mean, literally, it had been there for years. It was used everywhere, and it was very bug prone. And we were able to remove that pretty recently. But we haven't had as many generic ones. This one is actually, one of the key things about this is that this is really well suited to one-off tools and to reducing kind of the barrier to entry of one-off tools to be very low. But I think the other big use case we have for this is systematic migration from old APIs and old services to new ones. And so as we've had services that are sunset and we have new generations coming online, the teams responsible for those can actually migrate the entire code base and all of their users largely automatically. And that's probably the biggest use case we have.
So first, this is awesome stuff. But I had a question about the conflict resolution.
Yeah.
So certainly there could be like textual collisions, but there could also be semantic collisions. So
Yes.
do you guys resolve those?
So the question is, when we're running into conflicts, there are both textual conflicts, which are kind of straightforward, and version control systems have been dealing with those for a long time. There are also potentially semantic conflicts. The way we currently handle that is, in my opinion, a really bad form of brute force. So if there are textual conflicts, we give up and we tell the user. If there are semantic conflicts, we don't know. As I said, we haven't yet brought Clang into this reduce step. So we're not doing automatic verification. The other side of this equation, though, is remember when I said that we build everything from source every single time? That does make it a little bit easier for us to do verification on each iteration, but right now it is a separate step. We'd like it to be integrated in, but it's a separate step. Yeah. I think right now we have a few patches, but no, we haven't started really hacking on that. When I said the package up the rewrites, yeah. Oh, sorry, can you repeat the question? Yes. We've created a matcher language, but have we worked on enhancing the rewriter's interface to be easier to use? And the answer is essentially no. Thus far, we haven't really needed to, but I do think we will need to. We just haven't gotten there yet. Can I talk about some of the experiences building a new code base with Clang? I can. That's a very long conversation. Short version, ow. No. So I'll give you context. It's not ow because of Clang. It's ow because of a code base that had never seen Clang. If you have enough C++ code, if you have enough C++ programmers, a phenomenon emerges, which is that developers have no idea how C++ works. Like, they don't have the faintest idea, and so they do whatever the compiler accepts. And if you have a very large code base that was only ever compiled with a relatively lenient compiler such as GCC, you end up with an unbelievable amount of bad code. We spent, I don't know if it was actually 10 times more effort cleaning up our code as opposed to fixing bugs in Clang. It might have been more like 50 times more effort. Why do you think we started building this? To be clear, the first reason that we started building this was to update our code base so that it worked with Clang. The problem we had was that that doesn't work if Clang can't parse your code. So that didn't actually pan out as well as we had hoped. Chris, I think I speak for all the GCC developers when I say patches are welcome. Especially from you. Other questions, since we had that little off conversation.
In the renaming a method case, do you make any effort to look through comments or if that's out code?
When we were doing a transformation, the example given, as renaming a method, do we make effort to look through comments or if-def out code? And the answer is resoundingly no. I'm actually going to address these separately, though. So for comments, I don't think this is a problem, because we can't parse comments anyways any more than as just text, and we already have really good tools for searching and replacing in text, so we can update comments without Clang. If we ever get a Doxygen parser inside of Clang, that would change, but I'm still waiting, as Doug is, for that. If-def out code is a trickier equation. So there is no real way to parse if-def out code. It doesn't work. But if I can go back here, you'll note that I said 200,000 compilations. I didn't say 200,000 source files. One way around some of the problems with if-def out code is to just keep compiling it in every single variation you can imagine and record all of those and do the transformations on all of those. And as long as you have the deduplication logic worked out really well in the reduce phase, it all works. And this isn't just hypothetical, we have seen this actually work.
One of the interesting things that I just realized falls out from that is that you should be able to identify stuff inside of index which is never used.
We are actively working on dead code detection, yes. That would be awesome. Sorry, the question was we should be able to actively detect things, even inside of if-defs, that are unused, because we have a more global view of what gets compiled. And yes, we can.
So in your example where you rename the function, did you try to capture a situation where someone, rather than calling the function, was grabbing the function pointer so they can call it later, or call it directly and don't necessarily?
So the question is, when we're trying to replace a call to a function, do we actually handle the case of taking the address of the function in indirect calls? The answer is yes, but not in the code I showed you clearly. I was showing you one matcher. What we ended up doing when we're actually doing renames like this is that we write several different matchers to match each of the different patterns in which that particular interface is used. Because there are a lot more than just taking the address. Maybe we're calling it, maybe we're taking the address, maybe we're passing it as a template parameter, maybe it's just being used by a template implicitly. Some of the other cases that we ran into were times when people had actually taken the address of it, and it mattered what it was named because they actually used types composed out of preprocessor definitions, which is really, really unfortunate. So there are a lot of things that end up going into this. There have been hard-coded types elsewhere in the code base that we have to update so that the member function pointers actually make sense again. But at the end of the day, yes, we just have to write matchers for each construct we need to update. Yes? So that's the beauty of Clang, though. While it's pre-processed it, it's recorded every step along the way. So while you get an AST node and you see some name after the preprocessor ran on it, you can actually ask Clang, okay, what tokens led to that? What tokens before the preprocessor ran led to that? We can see when it's been token pasted together and where it came from and how to reconstruct it and how to actually apply the edits. And that's one of the really important things, because it turns out we actually have a lot of our code is inside of function style macro arguments. And so we have to be able to edit things even in the presence of a preprocessor. Yes? Okay, so I believe the question, and correct me if I'm misunderstanding, is after we go and we do a source-to-source transformation, we can try and compile it to make sure there are no syntax errors, but how do we handle the case when there are now logic errors? Funny thing about our build system, it also runs our tests. We can rerun every single test in the code base. Yes. So in the actual examples we have, we weren't just doing a rename, right? We're actually replacing a bad interface with a good interface. We're actually remapping arguments arguments with different types. We're transforming things in a much more complex manner. And what we would often find is that, not surprisingly, the bug-prone interface was used buggily, right? There are bugs in all of their uses. And so we actually would end up writing matchers to match specific bugs people would write with an interface and transform them back into the correct code with the new interface. And we have to kind of rely on testing and hope that we find all of them. We don't, and doing these types of things, the more involved the transformation and the more widely used the interface is, the harder it gets, and it gets to be very hard indeed.
Is the language expressive enough to be used as a basis for a static checker? For example, look at certain system calls, return value, making sure that they are checked against null before they are used as.
So the question is this language general enough to be used as a generic checker basis language? I think it might be useful as part of the checker language to identify certain patterns, but I think it's important to separate out the response and the identification. And this is a language designed to identify a pattern, sometimes loosely and sometimes narrowly, and what you do with it is separate. But probably, maybe, I would leave that to Ted, I think. Other questions? At the very back. How do we guarantee safety of the transformation? Well, we've already talked a little bit about this, and that's the idea of we can rebuild all of the code and make sure it still compiles, and we can rerun all of the tests to make sure those still pass. That gives us one layer of safety of the transformation. That's actually not enough. We actually had this problem when we were first trying to convince people that this was a good idea. We got a hilarious response from them. They looked at us and they were like, "I'm interested, but I don't trust robots." And we had to convince them that our robots are different. They're more trustworthy, right? And one of the really challenging things about that is how do you convince people that any tool knows the C++ language? It's hard to convince people that any person knows the C++ language. It's much easier to convince them that no person knows the C++ language. The way we did this was somewhat unusual. Our core thesis of this is that we trust Clang to be correct when looking at our C++ code. Not because we believe that Clang understands all of C++ or is perfect, but because we take Clang's understanding of C++, we use that exact same understanding to generate code for all that C++, and we use that code to run all of our tests. And if all of our tests, when they execute, match the expectations of the developer when they wrote the tests, then we believe that Clang understands the C++ code at least as well as the developer did. All right? Now, maybe that's not well enough, and we try and make Clang better all the time, but this is the only way we were able to convince a large group of people at Google that transforming their code with Clang was a trustworthy operation. Other questions? At the very back. Yes. Sorry, so do we make any effort to detect variable captures? I'm assuming you're meaning during a transformation. Okay, so the idea is that if we change the name of something and later on there is a name lookup, perhaps inside of a template, which previously would have resolved to that entity but now resolves to some other entity, but it still resolves, is I assume the tricky case, right? We've changed which overloads are selected for some template. And the answer is that yes, we did try and detect that. We would look not just at, we would look at all of the uses, which would include the template instantiation uses, and we would try and transform the underlying template as well so that both sides got changed at the same time. Oh, I see. Okay, so the question is actually in the case where there exist function calls that previously didn't resolve to this function and suddenly do resolve to the function. No, we do not try to detect that, and I am terrified if that ever happens. I think the good news is that we can detect that and without too much effort. It shouldn't be hard for us to start detecting that. However, shockingly, in transforming a very large amount of C++ code and doing ones that should have run into this, you would think, it never happened. So maybe we were lucky, but that's really lucky. So the question is, when doing these transforms, do we find outliers, things we weren't expecting as we start applying it to the rest of the code base and learn new things like new bad behavior, new bad uses, and overwhelmingly, yes. When I mentioned that it's really important we can iterate, like the time to apply the transformation matters, it's specifically because of that case. We will look for like, the 10 use cases that we know of, right? We'll write a transform that handles them, and we'll write a transform that should match any conceivable use case, but just dies if we run into it, right? And just tells us about those new use cases. And that iteration process happens repeatedly for some time as we discover new uses of the interface, new buggy uses of the interface. There are a lot of bugs that we found as we do these transforms. But I do want to be clear, part of that is just because we know we're changing a bug-prone interface. So it's not really surprising that we keep finding new and interesting ways people create bugs with it. Other questions? Will it ever be possible to use this language on Google Code Search? That's a really interesting question. I couldn't possibly speculate about products at Google. However, that's a really interesting idea. I know that we've announced we're turning off code search, but I also know that we've announced that there will be a code search service for projects hosted on code.google.com, and I still think this is a really interesting idea. Other questions? Any other questions? Am I not seeing people because of the lights? What they said. So the question is, what would it take to get it down to 1 minute? And I am not going to answer that question if it's okay. So Ted is rephrasing the question as how much of that time is build time and how much of that time is our tool? By build time, do you mean Clang parse time, or do you mean the infrastructure behind MapReduce?
I think it's more just like there's a minimum amount that you can't take out, which is compilation, parsing, and so forth. And is this just like a sliver on top of that, or is it like?
Okay, so the question is in specific whether the compilation, the existing compilation that Clang is having to do of the source code is a significant portion of the time. It is a significant portion of the time. It's certainly not all the time. If we made Clang 10 times faster, I don't think we would get to 1 minute. I can't talk about the size of our clusters. Okay, so the question is, are we scaling linearly with the number of machines we throw at this problem? And the answer is no, but not because of Clang, but because of MapReduce. If you read the MapReduce paper, they talk about some of the different scaling limitations as you change the number of machines in play. I actually am not a MapReduce expert, and so the published documents are actually the same ones I've read, and they talk about some limitations, and you can read them, and it's a more subtle problem. It's not something we can just throw machines at. It's more tricky than that. Any other questions? Awesome. Thank you very much.